Yep, I'm here.
Hi. So
Hi
Dana,
there.
just a very quick introduction. Dana is a professor at Monash University in Melbourne, Australia, and her main interests are human-robot interaction, learning full body motion primitives, and real-time safety in human-robot cohabitation. I think in the interest of time, I leave the rest to you. Thanks very much for joining us and preparing the presentation. The floor is yours.
Great, thanks, Hakim. Can you confirm that you can see my slides?
Yes, I can see them.
Great, thank you. So good morning, everyone, and thank you to Hakim and Luigi and the entire organizing team for proposing this workshop and for inviting me to present. I think this workshop topic is really important and really needed for effective human-robot interaction. So when Luigi invited me to participate, I was actually a bit worried about the long-term part of the workshop title. So at least in my research, we haven't yet been so ambitious to attempt to do long-term human motion prediction. So in this talk, I'm going to focus more on the near-term human motion prediction. I hope that will still be of interest to you and hopefully useful as building blocks towards longer-term human motion prediction in the future. So when we think about a human-robot interaction, for most of us, well before we encountered any real robot, we started thinking about robots through movies, books, cartoons, and other forms of fiction. And the robots of our imagination are not just capable of performing a variety of tasks, they can anticipate our wishes and cater to our every need. A key part of these capabilities is observing human behavior and actions and predicting, first of all, what will the person do next? And then second of all, what's the appropriate response from the robot? And so in this talk, I want to talk about how we can start implementing these two capabilities. So in the first part, I want to talk about how we can predict what the person will do next. And I will argue that in order to do so, it's helpful if we can estimate the person's objectives from their observed movement. And this is very closely related to learning from demonstration. That is learning robot behavior by observing a human teacher perform the action. And then in the second part, I want to talk about how we can predict human motion during human-robot interaction. And this is different than simply observing human behaviors because during the interaction, the human will be influenced by what the robot is doing and therefore may change their motion based on what the robot is doing. So thinking about prediction in the context of interaction is helpful both for just predicting what the person will do next, as well as what the robot should do in response. So let's start with the first topic, how we can estimate human objectives from their observed movement. As I mentioned, this topic is very closely related to learning from demonstration. So here is a typical workflow for these types of algorithms. We first of all need to measure human movement, and that could be using motion capture system or video or wearable sensors. And from that motion measurement, typically we will then estimate the pose at every time step. And as we are observing the human perform actions over time, that will generate a motion trajectory. So typically joint angles for each of the joints that we're estimating over time. Now, if we're observing a longer sequence of actions, then we also might want to perform temporal segmentation. So let's say, for example, we're asking a teacher to demonstrate how to clean up a kitchen table. So that demonstration might consist of multiple actions. So the person might pick up a cup, put it on the shelf, they might pick up a knife, put it in the drawer, and so on. And so in the temporal segmentation phase, we would extract each of those individual actions. And then what we want to do is from each of the action trajectories, we want to extract the objective of the demonstration. So note that in this class of approaches, we're interested to extract the control objective and not just to mimic the trajectory. And the idea is that if we can extract the objective, then we might be able to better generalize to maybe different environmental context or maybe different robot embodiment in the future. So this class of approaches are commonly known as inverse optimal control or inverse reinforcement learning. So what we assume here is that the observed trajectory was generated by an optimal controller in the central nervous system, and our aim is to infer the control objective. And then what we can do is we can, if the objective here is to learn from demonstration, is now once we know the control objective, we can then use that objective and maximize that objective to generate a control strategy for the robot to reproduce that motion. So most of these inverse optimal control or inverse reinforcement learning methods assume that this demonstration has been pre-segmented so that the cost function is constant within the time segment under consideration by the algorithm. And what we also typically assume is that we have access to the complete movement. So I can only estimate the objective once I've observed the complete segment. So we thought about whether we could relax some of these assumptions and whether we could actually use IOC-IRL not just for extracting the objective from a single action primitive, but also for segmenting the primitives. This work was led by Jonathan Lin while we were both at the University of Waterloo. So in this approach, we hypothesized that the cost function being optimized by the central nervous system is a sum of weighted basis functions or weighted features, and the weights change depending on the current action. So what we do is just kind of very simple. Initial approach was very simple. We just take a sliding window of a fixed size, and we just run it over the observed trajectory data. And in each window, we perform inverse optimal control to extract the cost function weights. And then if we observe that the weights are changing, then we assume that this corresponds to a change in the motion being performed, and therefore this should be a segment point. So we initially tested this with very simple motions, but then we were interested to see whether this could work for a more complex movement. And so in a study that was led by Kevin Westerman, we wanted to see whether we could apply it to this kind of complex full body motion that is a human jumping to a target. So this motion is interesting because it's a kind of multi-phase motion. So there is a takeoff phase where kind of the objective is to generate momentum. There is a flight phase where we're thinking about how to position the feet for landing, and then a landing phase that is focused on absorbing momentum. And we ran a study where we collected data from 22 participants, and we changed the difficulty of the jump by modifying. You can see here in the video, there's a target. So we modified the distance of this target from the starting point to make the jump either more or less difficult. And then we also recruited participants with different levels of expertise. Some of them were experienced parkour or nat move practitioners, and others were complete novices. And so what we wanted to see is whether we could use this approach to figure out, to both show the different phases and extract the cost function. So here is the results. Basically, this is the average over all of the participants. And what I'm showing here is a subset of the hypothesized cost functions and their relative weight over the duration of the jump. And the two black lines indicate the takeoff, the first one, the one that's right at 1, and then the second line indicates the landing. So what we can see here is that just by looking at these extracted weights, it's quite straightforward to extract the different phases. So what we see in the first phase, which is the pre-takeoff phase, the focus is on, the weight is high on the center of mass height and the center of mass velocity. So basically what's happening before takeoff is that the controller is focused on controlling the center of mass, takeoff, velocity, and position. Then in the flight phase, we see that the extracted weight is focusing on the position of the foot. So basically, we can't control center of mass position because you're just when we're in the flight phase, it's just projectile motion. And so what the control action is on bringing the feet forward towards the landing target. And then after landing, we see that the focus is on absorbing the landing impact. Now, in the IOC approach that I've described so far, we use a fixed size window to perform the inverse optimal control computation. So obviously, this makes our approach sensitive to the choice of window size. If we choose the window that is too large, more than one motion may be included in the window. However, if we choose a window to be too small, there may not be sufficient information in the observed trajectory to recover the weights correctly. So what we would like to do is to figure out what's the right window size. And so this work that was led by Wanjin Jin in collaboration with Shoshe Mo at Purdue and Sandra Kirche at TUM, we want to automatically determine the minimum required window to recover the cost function. So we formulated an approach that provides theoretical results to identify the condition under which the cost function is recoverable, which is a function of the system dynamics, the hypothesized structure of the cost function, and the observed trajectory. And so this allows us to identify the conditions under which the cost function is recoverable, detect when the cost function is changing inside a window, and then also process the data incrementally. So now we can finally get to what's interesting for this workshop is, okay, well, how can we now apply this to motion prediction? So the idea is that if we can perform inverse optimal control from incomplete trajectory data, then what we can do is we can start observing the motion. And once we think we have sufficient data for recovering the objective, we can then use that data that we've observed at the start to perform inverse optimal control. Now we have the cost function. So we can use that cost function together with an optimal control planner to predict what will happen to the rest of the motion. And so we have tested this with rehabilitation data. So in this figure, the dashed lines are joint angles and velocities. So in this case, joint angles of the lower body during the performance of rehabilitation movements. So the segment part that's shaded in blue is what we use to predict the rest of the movement. This is where when we predict that we have sufficient data. So the captured data is the blue dashed line, and then the prediction is shown in pink. So what we can see is that with our algorithm, we can accurately predict what happens in the rest of the movement. And if we use just a standard KKT-based approach that's shown in green, we cannot predict accurately, and this is expected because we're violating the assumption of the standard KKT approach that the entire trajectory has been observed. So with this approach, the key advantage here is that we can estimate the objective of the motion from a single incomplete observation. However, we rely here on, we assume that we know the cost function structure and that we know the dynamic model of the human motion performer. So now I want to switch tacks a little bit and move on to the second part, and that is to talk about predicting human motion during interaction. So this work was led by my PhD student, Tina Wu, and the project was done in the context of looking at how we can provide gait therapy for Parkinson's disease. So Parkinson's disease, or PD, is a progressive neurological disorder that results in motor disturbances. And a very common symptom is called freezing of gait. So in this situation, the patient has trouble initiating and sustaining a healthy, normal gait pattern. And it turns out that this symptom can be alleviated by providing cues to the patient on when to step. And there are 3 types of cues that can be provided. One type is a visual stimulus, so basically providing a line or some kind of indication on the ground on where a person should step, so providing a spatial cue. The other 2 types of stimuli are either auditory or haptic, so where either we provide like a sound like a metronome, or a haptic, so like tapping the person on the leg. And this provides a temporal cue that again can be used by the patient to improve their gait. So most existing approaches in the literature will generate this queue using kind of a fixed queuing strategy. There is no adaptation to what the user is doing. And what we wanted to see is whether we could develop an approach to do online optimization for queuing. And this was inspired by human-in-the-loop approaches that's been previously proposed for other types of gait rehab, and particularly for exoskeletons and prostheses. So here's kind of an overview of the system. So we're measuring the human movement using an IMU. And from those IMU measurements, we want to estimate basically the cadence. So what's the frequency of the gait? And then we want to, based on, we're also providing, we may be providing the person with a cue. And in this case, we use auditory cues, but of course we could be using haptic or even cues provided with an exoskeleton. So given the information about what cue we've provided and what the gait is, we want to learn a model of how the human is influenced by the cue. And then we want to use that model to then optimize what's the next cue that we should provide to generate the target gait. So the key point is what we want to learn is we want to learn to predict how the human will respond to our cues so that we can use that prediction model to choose our cues appropriately. So let me just quickly show you kind of the three key components. So first of all, our gait model is we're assuming that we're just dealing with periodic gait. And so that this we can model the periodic gait as a weighted sum of sinusoids, and we can learn those model parameters with incremental updates from IMU signal data. And so I'm showing some example data here. So this is the blue line in the top panel is the gyro signal from the walking, and then the orange is our estimate based on this weighted sum of sinusoids. And then in the bottom panel, we can see that we are showing the estimated phase in this periodic model and the estimated frequency. And in this data set, we are cueing the person with a metronome. And so we know what the target frequency is. And we can see that within 4 or 5 strides, the model converges to a fairly accurate prediction of the frequency. Then to learn this predictive model of how the cue influences gait, we use a Gaussian process to learn the mapping between the input cue frequency and the resulting cadence of the participant. And then using this GP model, we generate a cue that minimizes the difference between the target and the predicted cadence. So we're doing the learning of the model online. And so, of course, when we first start, we don't know anything about the model. And so since we're doing everything in the loop, basically what happens is that since we don't have a very good model, we kind of get these random cues. And those random cues cause the person to respond. And then once we have enough data points to see how the person responds to these cues, then we can start generating a more appropriate cue. And so that results in this kind of 2-phase behavior for this approach. And the first phase is the exploration phase. And then the second phase is the convergence phase. So we ran an experiment to see how this approach would work. So what we do in this experiment, we recruited 25 healthy participants. And we first asked them to wear an IMU sensor, that, as you can see on the right. And we don't provide any cues, and we just ask them to walk continuously in a large room in a kind of circular pattern, and we measure their baseline cadence. And then what we would like to do is we would like to see if we can cue them to increase their cadence by 20%, and that's the up condition, or decrease their cadence by 20% from their baseline, and that's the down condition. And we try to do this with 3 different strategies for each condition. The first is a fixed strategy where we just basically provide a fixed cue that is equal to the target cadence. A proportional strategy where the cue provided is proportional to the error. and then the adaptive strategy that's based on this optimization framework that I just described. And so the actual sequence of the conditions, we always start with the baseline condition, and then we randomize the conditions between the queuing strategy and whether it's up or down. And then after each condition, we also ask participants to complete a quick survey. So let me show you quickly some results. The first two panels here, I'm showing the target mean absolute error. So this is the difference between the target cadence and the observed cadence. And the four conditions are the fixed strategy, the proportional strategy, the adaptive strategy in the exploration phase, and the adaptive strategy in the converged phase. And what we can see here that for both the up and down conditions, we achieve the lowest error in the adaptive phase following convergence. And we also, on the right hand, we're also looking at the percentage of time that the controller is on. And what we can see here is that also the adaptive strategy achieved these lowest error while also having the minimum amount of time that the queuing was on. And this is important because if we have the queues on all the time, there is a danger that the person will habituate to the queue. So to summarize, in this learning from interaction framework, we found that performing this motion prediction is helpful for generating better queues because we see that the adaptive approach has the highest error during exploration, but the lowest after convergence. And why is this learning approach and prediction approach beneficial is because we find that there is quite, even for healthy participants, there is quite a individualized response pattern to the cues. So some people are very responsive to the cues and others are less so. And so therefore generating cues that are suited to each individual results in better performance. We also found that there is a higher cognitive load with the adaptive strategy, and this actually in the longer term might be helpful to bring attention to that task. So what we're thinking about in current and future work is, can we adapt this approach for longer term prediction? So can we use this kind of learning in the loop approach to also predict what happens over the longer term? So for example, is a person more likely to habituate to the queue or less? And then also, can we combine this approach with the approach that I was talking about earlier in the talk? So can it help us if we are estimating the participants' objectives and constraints to then also provide a better queuing strategy? I would like to thank all my students, collaborators, and sponsors, and I would like to thank you also for your attention. I'm happy to take any questions.
Yes, thank you very much. I'm wait a second, now I lost the window. So let's look at the list of participants. Oh, it's over there. So we don't have a hand raised at the moment. So then this gives me time to ask my question here. Very interesting the way that you actually predict motion from incomplete motion data. And I was wondering, you know, the curves that you showed there, the prediction was almost perfect. But whether it's also possible to derive a notion of uncertainty of this prediction in this way, or whether you have worked along these lines.
Yeah, that's a really good question. So in our case, we have a deterministic model, but we could certainly, a nice way, I think, to estimate the level of uncertainty would be to say, okay, we have a model where we've assumed a certain dynamic model and a certain dynamic model properties, so in terms of the mass and mass properties. And what we could do is we could say, okay, well, if we vary, if our model is imperfect and if we introduce variations in that model, how does that change our prediction? And then we also have an assumption about the cost function structure. And there again, we could say, well, if we now change that cost function structure, how does that change our prediction? And so we could generate kind of a family of predictions and see what the range is, and that could give us an estimate of the uncertainty.
Yeah, that's very interesting. So have you already worked on this, or that's kind of your online take on the problem?
Yeah, we haven't worked on this. So one thing that we have been working on is kind of more that's looking more in the direction of individualizing, is kind of incorporating this idea, because much of this work that we're interested in is working with patients, is kind of this question of how do we individualize the model. And so for for healthy participants, we can rely, when we're coming up with this dynamic model, we can rely on very nice anthropometric tables and so on. But when we're dealing with patients who may have much greater kind of left to right asymmetry, then these kinds of models may not be appropriate. So we're definitely, this is one of the things that we're working on, is thinking about how this can be adapted to patients.
Okay. Thank you.
I would have a question maybe from my side, and it's really related to the last topic, Luigi, here. We were also saying at the beginning of the workshop, right, maybe we should think about also how do we end failure cases. And now in your work, right, you are directly working with patients, right? How can you make sure that, if you have a wrong prediction, everything will be handled properly? Do you have like hard constraints that controllers should always satisfy, or do you manage this in a more elaborated way?
Yeah, actually, that's a great question, Luigi, and I'll maybe actually talk about the second project, because in the second project we're kind of directly using our prediction to then drive, how we're going to cue the person, and the example that I showed was with using auditory cues, but we would also like to do this with exoskeletons, where we would also kind of generate a force on the participant. Actually, I was one of the alpha participants before. I'm not included in any of the results, but I tried the system on myself. And so when you're actually in this, like before you actually have a good model, when you're in this exploration phase, and the system generates these kind of random inputs, it can actually be quite disturbing, because you're being asked to move faster, move slower, and I think if it was an exoskeleton especially, this would be quite jarring. Definitely this kind of exploration phase before the model is well known is certainly very risky. And so what we've done is just kind of a very in the exploration phase, there is a band of allowable inputs. But certainly when we're, this is with healthy participants, but certainly when we're dealing with patients, this band would probably be narrower. And then probably what we would want to do is we wouldn't want to just, learn from nothing. We would want to start with some model that we had collected from healthy data. So already start with a fairly good model before starting the interaction.
Thanks.
So there is a question, and since we're a little bit already over time, this has to be the last question, but please, Alexander.
Thank you. Great talk. Fascinating work. I have a question about the Parkinson's disease also project. Do you have also the technology to monitor the evolution of the disease with this sensing technique?
Yeah, so I have some other work, I didn't talk about it here, where we have done some work looking at tracking Parkinson's disease symptoms just from wearable sensors that can be worn all day. And that's also quite a challenging topic, especially. So there are kind of two approaches. One is that a lot of times when Parkinson's patients, PD patients come into the clinic, they're asked to do kind of a specific movements that are kind of like a clinical protocol. But of course, when people are at home, they're just doing their everyday movements. And what we would really like to be able to do is to be able to estimate their symptoms during their entire day, and not just when they're performing these specific movements. And the reason for that is because a lot of PD patients are on a medication schedule, which is, so there's a kind of half-life, and they generally report that their symptoms will be better a certain time after taking the medication, and then they will get worse as the kind of medication wears off. And so, yeah, so we have some work that I didn't talk about here that's looking at basically, can we learn what is a typical signature of a PD patient? And that was actually we used a learning-based approach where we try to, based on a data set that we collected with clinical partners, where we actually had data from a clinician that had, so the participants, the PD patients were wearing sensors, and they were also followed by, during their everyday activities, followed by a clinical experts who was labeling the data.
This was my follow-up question. Is this data publicly available or unfortunately?
Yeah, unfortunately, this was collected at the clinical partner, and they did not give us permission
sharing it,
to share
yes.
the data. Yeah.
Thank you. Thank you very much.
Okay, this brings us to the end of the first part. Thanks again to both of the speakers. Very nice start to this workshop. And now I hope, since we are a few minutes late, that you all have